Go ahead and start our last section in chapter 4, section 4.5. And in this section, I just want to show you a few applications of exponential functions and where you might see these again. These have a lot of applications to science in particular. So if you're a science major, you might see some of this stuff again in some of your science classes. But we're going to look at the basic sort of general model. This is in the guided notes, so make sure you have these before you start the video because I think you'll want to fill these in as we go. The general model for an exponential growth or decay function, I'll explain what I mean by that in just a second, is given by this expression. So it can be written one of two ways. The first way is written in function notation. F of t equals a, and that little subscript, I call it a naught. So a naught e to the kt power, or just a equals a naught e to the kt power. So this is sort of the general model we're going to follow with most of these questions. So what do all the variables stand for? K is what represents your rate of change per year, per month, per day, whatever unit of time, T is time, that you're working with. So if K is positive, then the function models the amount or size of a growth entity. So in other words, something that's growing or increasing in size. Think population of a country, that would usually be increasing in size. So K would be positive in that case. A naught stands for the initial or the starting value for the population or whatever it is we're looking at in the problem. And that would be the value of the population or whatever our quantity is at time t equals 0. So the initial value occurs when we start measuring at t equals 0. And then A is the amount at any given time t. So say after t is 5 years, for example, we would have a starting amount, we'd know our K value, we'd be able to figure out the amount, A, after so many years. K is a percent, so it's always going to be some sort of percent. We're going to be using it in decimal format. That's always a percent representing the amount of growth. So if K is positive, it's a growth entity, so the amount of growth per year. And I say per year, it could be per day, it could be per month, it could be per hour. The unit of time can vary depending on what the application is, but per whatever the unit of time is. K is that percentage of growth, okay? If K is negative, on the other hand, then we have a decreasing model. So if K is negative, the function models the amount or size of a decay, or you can say decreasing model. So if K is positive, we have an increasing function. If K is negative, we're going to have a decreasing, or what in science we might call a decay entity. Everything else is the same. A naught is the initial value or size at t equals 0 when we start measuring. A is the amount at a given time t. And once again, K is a percentage. And it's going to be in decimal format, but it's a percentage representing the amount of, I'm going to say decrease, amount of decrease per year. Or like I said, per day, month, whatever unit of time that you're working with, okay? So what would these graphs look like? Well, let's do the first one. If K is positive, we said that was going to be a growth model. So if K is positive, then we're going to have an increasing exponential function. You remember exponential functions, we said they normally go through 1 on the y-axis. In these examples, though, they're going to go through on the y-axis. The y-intercept is going to be whatever the starting value is, a naught. So that's going to be your y-intercept. And if it's a growth model, it's going to be an increasing function from left to right. And we should label these axes. The x-axis is your time t. The y-axis is your amount a, whatever that is. Now, in reality, we're not going to have negative time values. So the only part of the graph we would be interested in is from that initial amount onwards as time progresses. If it's a decay or a decreasing function, so that in case K would be negative, that's how you would know it's a decay problem. We're still going to have our initial value as our y-intercept, but instead of increasing from left to right, now it's going to be decreasing from left to right. The x-axis is still their time, and the y-axis is still your amount, A, whatever that is that we're measuring, okay? And again, we're only going to care about when time is positive, so this left half of the graph we're not even going to really do anything with. All we're going to worry about is from the initial value out. Okay, let's start with an application looking at population. So the population growth of a country, or in a continent in this case, we're looking at Africa. So make sure you have your calculator out because you're definitely going to want that to help you with these problems. So it says in 1990, the population of Africa was 643 million, and by 2000, it had grown to 813 million. So it says use the exponential growth model function, so the formulas we were just looking at, in which t is the number of years after 1990 to find the exponential growth function that models this particular data. Okay, so let's write the formula down. So it's A equals A naught E to the KT. That's the formula. And so our job is to fill in A naught and K. T and A are going to be variables in the equation, but we need to find A naught and K. Well, A naught, remember, is the starting value. So we started measuring this in the year 1990. So according to the question, what was the population in the year 1990? And so the population in that year was 643 million. So that's going to be our A naught value. So we're going to start measuring in 1990, and that year the population was 643 million. So remember, A naught is your starting value or your starting amount. All right, so now we still have to find K. We have to figure out what the percent of growth is per year. And that's where the second piece of information that they gave us comes into play. It says by the year 2000, the population had grown to 813 million. So think about if 643 million corresponded to t equals 0. We know it was 1990, but we said that was the initial year we started measuring. So 1990 would correspond to t equals 0. Think about what p-value would correspond then to the year 2000. In other words, how many years after when we start measuring is the year 2000? And that would be 10 years because that's 10 years since 1990. So when t is 10, the population, the amount A, has gone up to 813 million. So let's substitute these numbers in for the A and the t value, and that will allow us to solve for K. So I'm going to put in 813 in place of the A. 643 does not change. That's your starting amount. That's the same starting amount throughout the entire question. E to the K, I don't know, but I know that after 10 years has passed, my population's up to 813. And so now what we have is an exponential equation where we can solve for K. So I want you to think about what we were doing in section 4.4. We were solving exponential equations. The first thing we need to do to solve for this K is to get that 643 out of the way. So I need to get that to the other side so I can isolate the exponential part of the model. So I'm going to divide both sides by 643. So we're going to cross that out, and I'm going to use my calculator, and I'm just going to get a decimal approximation for 813 divided by 643, just so we don't have to deal with fractions. Make sure you leave a few decimals in your answer. Let me come over here and write where we're at. I'm getting a decimal. Check my math with your calculator as well. I've got 1.264 equals e to the k times 10 power. And so now my job is to get this into a form where I can solve for k. So I've got an exponential equation. So remember we said when we have an exponential equation, the way to get the variable by itself, if it's in the exponent like this, is to rewrite this in logarithmic form. So the base for this is e. So we can say log base e of the other side. So don't let the way it's written fool you. It's always log base e, whatever the base is, of the other side, which is the 1.264, equals the exponent, which is k times 10. Normally we don't write log base e. Instead, we write natural log. And we're going to use natural log for all of these because they're all going to be base e. Okay, so where am I at? I've got the natural log of 1.264 equals k times 10. And so I'm going to divide by 10 to get the k value. And so this is where the calculator is really important. I need to get that k value. So let's go ahead and put this into the calculator. So we have the natural log of 1.264, close the parentheses, and then divide that number by 10. And I get a k value of approximately, let's use 4 decimals here, 0.0234 it looks like. Okay, and remember this was a percentage, right? So this is the decimal form of a percentage. If we were to change this back to percent, this would be about 2%, 2.3%. The population of Africa was growing 2.3% per year during that time period. So the model, they wanted the model for this. So the model we're going to use is A equals 643E. Now put in that K value. That's going to be the same throughout the problem, 0.0234 T. So A and T are going to be the variables in your model. So this is the model right here that represents the population change for Africa. Now part B says, by which year will the population reach 2 billion? So what variable are we solving for this time if we're looking for what year the population will reach 2 billion? So 2 billion, let's just do a little bit of refresher on these big numbers here. 2 billion, a million is 6 zeros, so 2 billion would be 9 zeros. So this is 2 billion right here. Remember though, I used 643 million. So when I put my numbers into the problem, I was working with millions. So if I want to know how many millions this is, I need to move this over 6 spaces, and that would give me 2,000 million. So that's the question they're asking. When will the population reach 2,000 million? If that part's a little fuzzy to you, do not stress about it. I'm not concerned about whether you recognize what 2 billion is or whatever. That's not a big deal. Take my word for it. They're asking us when will the population reach 2 billion, which is 2,000 million. What I do want you to pay attention to is how we're going to solve this equation. So remember, the year is what we're looking for. So I'm going to put 2,000 in place of the A because 2,000 is the population I'm trying to get to. So 2,000 equals 643E to the 0.0234 T. And so now I'm trying to solve for T because I'm looking for the year. So we're going to divide by 643. I'm going to get my calculator and I'm going to get a decimal for that. So that gives me 2,000 divided by 643. And so that gives me a decimal of 3.11, I'm going to say 04. More decimals are always better for these. Equals e to the 0.0234 t. Okay, now I need to solve for t. So I've got an exponential equation here. So we're going to change it to logarithmic form. The base is e, so I'm going to go ahead and write it as natural log of the other side, 3.1104 equals 0.0234 t. And then last but not least, to get t by itself, I'm going to divide both sides by 0.0234. And then we're going to get a t value. Let me come up here and write it. We're going to get a t value of, let's see what our calculator tells us. So make sure you see what we're doing. We're doing natural log of 3.1104, close parentheses, divided by 0.0234. And it's going to take about 48 and a half years, it looks like. So about 48 and a half years to get to that population. Now, have we finished the question? It said, by which year will the population reach that magic 2 billion number? We know it's going to happen in 48 years since we started measuring. So to get the answer, to get the year, I need to add 48 to the 1990 because that's when we started measuring the population. So to get the year, we're going to do 1990 plus that 48. And that puts me in the year 2038 and a half. You could say 2039, that would be acceptable. It really doesn't make a big difference. Okay, the process is what we're focused on. Let's look at the next example. If you are a science major, you'll see this again when you take chemistry, or if you took chemistry in high school. You may have talked a little bit in chemistry classes about something called half-life. And so we're going to look at the half-life of a substance and how that's measured. So the half-life of a substance is the time required for half of a given sample to disintegrate. A process called carbon-14 dating is used to calculate the half-life of fossils and artifacts. After 5,715 years, a given amount of carbon-14 will have decayed to half of the original amount. So let's be clear on what we mean. The half-life for carbon-14 is 5,715 years. So that's standard for carbon-14. And it's just a measurement that scientists know. So what does that mean? Well, that means if I started with 100 grams of carbon-14, after 5,715 years, I would be down to half of what I started with. So if I started at 100 grams after this many years, I would be down to 50. If I started with 1,000 grams after this many years, I would be down to 500. Whatever I start with, it's going to take this many years to disintegrate down to half. So elements disintegrate in chemistry. And so that's what we're talking about. So the question says, find the exponential decay model for carbon-14. In other words, they're asking us to figure out the K value. So the K, remember, was the percentage per year that it's going to decrease. So let's start with the basic equation. A equals A naught E to the KT power. They did not give me a starting amount. But if I know the half-life, it doesn't really matter what I start with. I'm going to use that time to substitute for T, and whatever amount I start with, I'm going to have half of it after that many years. So let's pick a starting amount. It makes absolutely no difference what we choose. I'm going to select 100, just because I feel like 100 is an easy number to work with. So I know that K, of course, is what I'm solving for. I know that after 5,715 years, because that's the half-life for this element, what is my 100 grams going to disintegrate down to? Well, it's going to be cut in half, so it's going to take me down to 50 grams, okay? I'm going to divide both sides by 100 so that I can solve for K. So 50 divided by 100, of course, is 1/2. And you see, that's why I say it doesn't matter what you started with. If you put your half-life time in your equation, whatever you start with, you're going to put half of it on the other side. You're going to get 1/2 here every time, so it makes no difference. Now I need to solve this equation for K. So I'm going to write it in log format. So natural log of, natural log of 1/2 equals 5715 times K. And then to solve for K, I'm going to divide by 5715. And this is a little bit messy, so let me cover the next question up so I can have some space to write. So I'm going to divide by 5715 on both sides. Now think about, should your K value be positive or negative in this example? Well, it's a decaying entity, so that means K should be a negative percentage because it's going down. So in my calculator, we're going to put in the natural log of 1/2, and I'm going to go ahead and make it 0.5. Well, I'll do 1/2, doesn't really matter. You can make it 0.5 if you want to. Natural log of 1/2 divided by 5715. So that's our K value, or I'm sorry, that's our time that we're dividing by. And look at what I've got. Now make sure you understand what this means in your calculator, particularly if you have a scientific, a graphing calculator. This is scientific notation. And so this little E, this capital E here, means that this is scientific notation. So if we were to write this in scientific notation, we would have a K value. And by the way, you see that it's negative. That's important. We said it would be negative. So it's negative 1.2129. Use at least 4 decimals when you use that K value, times 10 to the negative 4th. All right, so that E, capital E, -4 means times 10 to the negative 4th. So that's our K value. So our model for this is A equals A naught E to the negative 1.2129 times 10 to the negative 4th T power. So that would be the model that represents the decay rate for carbon-14. And we could use that to estimate the age of fossils or artifacts or Dead Sea Scrolls in the next example or whatever, okay? So let's take a look at the next example. It says, in 1947, earthenware jars containing what are known today as the Dead Sea Scrolls were found by a group of Arab herdsmen. Analysis indicated that the scroll wrappings contained 76% of their original carbon-14. Estimate the age of the Dead Sea Scrolls. So let me write my model again. A equals A naught E to the negative 1.2129 times 10 to the negative fourth T. So this is the model, okay? So here's the deal. We don't know the initial amount of carbon that was in these dead sea scrolls. Because they gave me a percentage of whatever the original amount was, it's not going to matter what I use for the original amount. The other side, so I can put in a value here for A naught, the other side is going to contain 76%, and that's what we're going to use to solve for T. So pick an easy number to work with. If I'm working with percentages, I think 100 is probably an easy number to start with. So I'm going to put 100 as my original amount. E to the negative 1.2129 times 10 to the negative fourth, that's the K value. T is what I'm solving for because we're looking for the age. What's going to go on the other side? So by the time we found these dead sea scrolls, how much was left? 76% of the original amount. Well, if 100 is my original amount, what is 76% of 100? That's just going to be 76. And now we're going to solve this equation for T because remember we're looking for the age. So I'm going to divide both sides by 100. And so that gives me 0.76 equals E to the negative 1.21 times 10 to the negative fourth T. And just like all the others, I need to switch this to logarithmic form. So I'm going to go ahead and do that. And since it's E is the base, I'm going to use the natural log. So we're going to have the natural log of 0.76 on the other side. I'll put parentheses around that just to kind of group it. Equals negative 1.2129 times 10 to the negative fourth T. And we need to solve for T. So the way we're going to do this is we're going to divide by that K value, that ugly number right there. So let's go ahead and do that. Like I said, you really want a calculator for these problems because you're going to need it to do calculations like this. So we're going to divide both sides by that number. That's in scientific notation, negative 1.2129 times 10 to the negative fourth, and that'll get the T value by itself. So we can estimate how old we think these are. All right. So let's go to the calculator. Let's look at what we're putting in the calculator. All right. So we're going to do natural log of 0.76, close that parentheses, divided by, open the parentheses again, negative. So make sure if you're using a graphing calculator and even a lot of scientific calculators, the negative key and the minus key are different. So I'm using the negative key at the very bottom. So negative 1.2129. And then for the scientific notation, I can either type in times 10 to the negative fourth, or I can use this capital EE key. That's the calculator notation for scientific notation. So if I do second comma, that little E pops right up. And then you can just type in negative 4. And the calculator knows that you mean times 10 to the negative fourth. Hit enter, and we get a value of 2,260, about 63 years old. So our time, let me put this back up here so everyone can see it. So our time is about 2,263 years old. So when these were found at that time in 1947, they were about 2,263 years old. Okay, let's take a look at Ron studying a bacteria in AP biology. He's calculated that the K value is 0.658. So that's a pretty large percentage. Think about that. Remember, K is percentage. This is growing at about 65.8% per hour because time is measured in hours. The question says, how long would it take for 15 bacteria to grow to 250? So they've already calculated the K value for us. That's the hard part. So let's write out the model using the K value and the starting amount. They gave us a starting amount also of 15. So A naught is going to be 15. E to the 0.658 T. And that's the model that we're going to work with. Now the question said, how long? So we're looking for time. Will it take to grow to 250? So I'm going to put 250 in for the A value. And we're going to solve
for t. So this is a good question. This one I don't think is too difficult. I think this would be a good one you might see on a test or something where you've given the k value and you just have to work with it to solve for the time or whatever it is they're looking for. You may want to pause the video and go ahead and work through this and see if you get the same answer as I do. So first thing I'm going to do is going to divide by 15 because I got to isolate the exponential function part. So 250 divided by 15, if you want to use a decimal for that, you can. If you want to use a fraction, that's okay. As a decimal, I'm getting 16.6, it's 667, it's repeating is what it is, a repeating decimal, equals e to the 0.658t. And then I need to switch it to logarithmic form. Once again, the base is e, so I'm going to use natural log of 16.667 equals 0.658t, and then we're going to divide both sides by 0.658, and we're going to calculate that and see what we get for time. So in the calculator, we're going to have natural log of 16.66666, whatever, just put in a bunch of sixes there, close parentheses, divided by 0.658, and I'm getting about 4.28. And remember, this was an hour, so it's going to take about 4.28 hours for the bacteria to grow from 15 to 250, okay? All right, so last example here, we're going to take a look at a half-life question again. So it says the half-life for the element tritium is 12.32 years. And the question says determine K, the rate of growth per year for tritium. So we're going to use the same formula. A equals A naught E to the KT power. And what we're asked to find is K, the K value. We're going to use the half-life to help us figure that out. So remember what half-life means. That means it takes 12.32 years for whatever amount we start with to be cut in half. Now, they didn't give us a starting amount, but it really doesn't matter. Pick a number that's easy to cut in half, basically. You can use any number you want. I like to use 100. So remember, if A naught is your initial amount, I'm going to pretend 100 is my initial amount. I have 100 grams of this substance, let's say. E, of course, is the constant E. K is what I'm solving for, but I know that after 12.32 years, so that's your time, right? 12.32 years, what is that 100 going to be cut down to? Well, this is the half-life, so that means it takes that many years for the 100 to be cut in half. So after 12.32 years, the amount of the substance that I'm going to have would be 50, because 50 is half of 100. Like I said, it does not matter what you started with. You could have started with 1,000. After that number of years, you'd be down to 500. Makes no difference what you start with, but just make sure you take that initial amount, you cut it in half if you're using the half-life time that they have to give you. So we're going to solve for K here. We're going to divide by 100. We got to get that out of the way first. Cross those out. So we have 1/2 equals E to the, I'm going to write this as 12.32K just because it looks a little bit nicer. And then we want to switch this to logarithmic form. It's base E, of course, so we're going to use natural log of 1/2 equals 12.32K. We're going to divide by 12.32 on both sides. And then we have to use a calculator to figure this out. Now think about your K value. Should it be positive or should it be negative? Well, remember that depends on what the substance is doing. If we're talking about half-life, the substance is decaying, so the K value should be negative. So let's practice putting this in the calculator. So I'm going to go natural log of 1/2. Make sure you put parentheses around that 1/2. That's very important because you just want to take the natural log of the 1/2. You want to get that number, and then you want to divide it by the 12.32. And notice we get a negative value, so we get K equals negative point. They didn't tell us how to round it, so I'm just going to round it to 4 decimals, 0.563 it looks like. So that's the percentage per year that this element is decaying, about 5.6%. And notice that it is negative, right, which is what we said should happen because it's a decaying element.